All right, so let's see who's here. Danny's here, Eric is here. I said hi to Kendall. Who else is here? Katja's here, Nick is here, Ronnie's here, Edwin's here. Good to see you, Nick. Hi, Edwin. All right. Hey, today, can you imagine in August when you started this class that you would know how to or understand how to prove square root of 2 is irrational? Well, today you're going to see that proof and you're going to understand it. And I just think that's exciting because it's not a trivial concept. So let me just go through some announcements with you. And there are preliminary notes up, uh, but it's a tiny bit different for this class, of course, because of the two different testing rooms. So these will replace those. Test 2 is Monday. And these are the sections that it covers, and that's stated in the syllabus. I've made a few small adjustments to the reading page. I've updated, of course, the Blackboard calendar with the due dates of everything. If you're at Tune, the room you're going to take test 2 in is room 213 instead of 214. So it's next door to the room where you took it, test 1. And for TU students, it's the same room that we were in last time. It's room 320. And I'll put up the sign and make sure the door is open and everything to the math department. So there is a mini homework that I need you to work so that I can grade that and get it back to you. It's just 2 problems, and it'll help reinforce your understanding of proof by contrapositive, and it'll also check and make sure you understand the way that proof by contradiction works. But like I said, it's just 2 problems. There won't be any WebAssign extensions on test 2 material after you take test 2, right? The point is that you're supposed to do the homework before the test. But I did make the due date for homework 4748 Saturday instead of Thursday, just to give you a couple of extra days since you're going to be working on this mini homework. And then there'll be one more WebAssign, and it'll be due right before the test. It's just it'll be part of 5-1. We're going to cover part of 5-1 on Wednesday, and that will be on the test. But it's fairly easy stuff, and you shouldn't have any trouble with that. The WebAssign should suffice there. Any questions on our schedule? Okay. Our goals today are to finish 4-7 and work a proof from 4-8, which is to prove the square root of 2 is irrational. We're going to compare the proof methods that we've learned so far. Of course, the new proof method is called proof by contradiction. And if you've done any reading at all in the book, you may have seen that coming. We're going to use a fact tonight, and that is that the reals are divided into 2 subsets that are disjoint from one another. They have no elements in common, the rationals and the irrationals. The fact of the matter is, if x is a real number, then x is either rational or x is irrational. It's going to be one or the other. It's kind of like when we look at integers, an integer is either even or odd. It's got to be one or the other. It can't be both. Okay, or an integer n greater than or equal to 2 is either prime or composite. It can't be both. Okay, I'm gonna move this back just a little bit. All right. So I'd like you to think about this statement. It's an if-then, so it's universal. If x is rational and y is irrational, then x plus y is irrational. So if you were going to prove this using direct proof, And I hope everybody in here knows the direct proof method. You seem to understand it fairly well. Um, I've noticed homework is sort of interesting. Grading homework is sort of interesting. People do either really, really well, right? Or it seems like a bunch of you aren't doing the homework at all, the special homework. I'm concerned about that. If you want to talk about it after class, please stick around and we can talk about that. But if you were going to prove this statement using direct proof, one, can you state the hypothesis that you would take? Just write down what you think the hypothesis would be. Take a minute and do that. And for direct proof, state what you wish to show. Take a minute and do that. Oh, good. Ahmed's here. Gabriel's here. Hussein is here. Fantastic. We got a full house. So after you state what you wish to show, let me ask you this. What work could you do that would allow you, what work would allow you to show you attained that which you wish, or that wish that you state in part two? So let's have a little discussion about this. Obviously, I want to motivate you to understand that we need a proof method to deal with this. So if x is rational and y is irrational, then x plus y is irrational. So anybody want to offer up what the hypothesis would be? And I'll open the chat too if you don't feel like micing in, but feel free just to mic in. What would be the hypothesis for a direct proof?
X is rational, Y is irrational.
Yeah, we assume the hypothesis that x is rational and y is irrational. Good. What would we wish to show?
X plus Y is irrational.
Exactly. We wish to show x plus y is irrational. Oh, good. Thanks for chatting in too. That was Eric that chatted in too. So, folks, what work would we be able to show that would prove that something is irrational? Do we have any kind of definition of irrational other than it's not rational? We don't. Do you know of any equation that we could prove holds that would help us prove something is irrational? There isn't. There is none. All we know is that x plus y doesn't equal a over b for any a or b that are integers. It's like we know a whole lot of stuff that doesn't happen, but trying to prove something is irrational directly is extremely tricky and way beyond the scope of this course. In fact, folks, in my entire mathematical career, I've really only seen one proof involving irrational numbers that actually digs into the idea that it's got an infinite decimal expansion that never repeats. So to try to prove this directly is very problematic. Because for one thing, look at our hypothesis. X is rational. Okay, great. We get one equation from that, right? X equals A over B. But the hypothesis that Y is irrational gives us nothing, gives us no equations at all. And then we have the same problem if we're trying to prove x plus y is irrational. There's no equation that we can say, hey, we can point to that and say that means it's irrational. We don't have anything like that. And that's sort of the nature of the irrationals. So let's think about this, and let's think about the logic behind a proof by contradiction. Like, we need another proof method. Even proof by contrapositive would be really tricky, because then we would assume x plus y is rational, but then we would have to be proving that x is irrational or y is rational. And that's also very difficult. It's possible, but difficult. So here's the logic behind proof by contradiction. I'm actually just gonna put this up so we can talk about it. Just suppose you want to prove a universal statement of this form. It'll either look like something like for all x and d, if p of x, then q of x. Or if we have two variables, it'll look like for all x and d and for all y and f, if p of xy, then q of xy. Okay, these are just two kind of basic forms of universal statements. So the logic behind proof by contradiction goes like this. For a proof by contradiction, we're going to do 3 steps. In step 1, we're going to assume the negation is true. Okay, so we'll take the negation of a for all if-then statement. Then we're going to use definitions, logic, and algebra to show this assumption leads to something that's impossible, called a mathematical absurdity or a contradiction. Do you remember contradictions in tautologies? Contradictions were statements that were always false. Tautologies are statements that are always true. So a contradiction, here's some examples. 0 equals 1. It's always false. Okay. X is greater than X. Impossible. A number is both prime and composite. Impossible. A number is both even and odd. Absurd. A number is both rational and irrational. Impossible. Okay, see, so you get the drift of what some kinds of contradictions would look like. Then step 3, since the negation leads to a contradiction, we conclude the negation is false. So the original statement must be true. Okay, so that's the logic. Assume the negation, show that leads to something that's impossible, conclude the negation therefore must be false. So the original statement is what has to be true. And this hinges on the idea that statements are either true or false. All right, so let's just go ahead now and look at this proof. Or maybe I'll write the statement one more time. Yeah, let's look at the statement. So it's a for all. It's a for all x and y in the reals. Even though that wasn't said, it's implicit. If x is rational and y is irrational, then x plus y is irrational. Okay, so if we, parse this thing out, This is P of XY, that X is rational and Y is irrational. And Q of XY, the Q, is that X plus Y is irrational. So it's an if P, then Q. Okay. So in our proof by contradiction, we're going to assume the negation. By the way, just like when you write a proof by contrapositive, when you write a proof by contradiction, you always let your reader know what you're doing. Otherwise, your reader is going to be completely confused. So what is the negation of this statement?
X is rational and Y is rational and X plus Y is rational.
Okay, did I hear you right? Did you say X is rational and Y is irrational, or did you say Y is rational?
I'm not sure which one I said actually, but
Which one do you want to say?
Y is irrational.
Correct. We want to keep the hypothesis just like it is because the negation of if P then Q is P and not Q. And of course, this quantification changes from for all to there exists. Everybody with me? Okay, so here we go. We're going to assume there exist real numbers, X and Y, such that and again, just to remind, we're looking for P and not Q, right? So such that X is rational and Y is irrational and X plus Y is rational because the negation of X plus Y is irrational is that it's not irrational. And that's the same thing as saying it is rational because real numbers are one or the other. Now, let's just take a look at what we have now to work with. Because a minute ago with the original, all we had was a single equation because X is rational. We didn't get an equation from Y being irrational, and we have no clue about an equation that would help us prove X plus Y is irrational. But now, suddenly, we've got that X is rational. That's going to give us an equation. We also have that X plus Y is rational. That's going to give us an equation. But as you know, we need to use the whole hypothesis. We're still kind of stuck with this hypothesis that Y is irrational. Well, folks, the only way we can use that is the way we're going to use that information. That's what we will contradict. We will use the equations that we get from X being rational and X plus Y being rational and do some sneaky algebra and we'll solve for Y. And we will show that these two things force Y to be rational, which will contradict this assumption that Y is irrational, because that's really the only way we can use that assumption is by contradicting it. Questions before we get started? So we wish to show a contradiction occurs. That's always the wish when we're writing proof by contradiction. All right, here we go. By the definition of rational, we know. I'm going to space things out. X is equal to A over B. Of course, there are three parts where A and B are integers and B is not equal to 0. And we also know X plus Y is equal to, say, C over D, where C and D are in Z and D is not equal to 0. So we've got, good stuff here. We've got really a lot to work with. All this stuff. Okay. All right. So the question is, how do we find the contradiction? In fact, we wish to show Y is rational to get a contradiction. So there are several ways to do this. My favorite way to kick this kind of proof off is to just state a tautology, something that's always true. How do I decide what tautology to state? Well, I look around, I look for the bigger expression, the expression that has both the X and the Y in it, okay? So that's the X plus Y. And I just notice, hey, X plus Y is equal to X plus Y. That is a tautology. Now, why do I do that? Because I know I have an equation that I'm going to be able to plug in, expression A over B that I'm going to be able to plug in for X. So I'm going to put the square brackets around it just to kind of help you realize we're going to substitute in there for the X. Over on this side, if we think about that whole expression X plus Y, well, we've got an expression for that we'll be able to substitute in. See where this is going? We're going to be able to solve for Y. So, i.e., here we go. A over B plus Y is equal to C over D. I just substituted in A over B for X and C over D for X plus Y. And now we can solve for Y. And it turns out, of course, Y is going to equal C over D minus A over B. And we can kind of do this in one fell swoop. You can do it in 2 steps if you need to, but it's just, it's sort of an algebra we've already done now. We've practiced that algebra with adding or subtracting 2 fractions. Subtracting is no big deal. So that is part 1 of the definition of rational. We've got Y looking like an M over an N. So now all we got to do is finish verifying that Y is rational by satisfying or showing that the second and third parts of the definition of rational are being taken care of here. We'll take care of those. By the way, I noticed in homework that almost everybody is able to write the definition of rational, if you're given that something is rational in the hypothesis, and that's great. People are writing all 3 parts. Yay. I am noticing a few people are not addressing parts 2 and 3 of the definition of rational to finish really nailing the idea that, in this case, Y is going to be rational. So we really have to, watch our wording and make sure that we nail this because we want to show that Y is rational. So here we go. We'll continue this. So here we go. Since I'm going to say it using the closure properties. Since Z is closed under addition and multiplication. No, it's not addition. What are the operations being used?
Subtraction.
Subtraction.
Yeah, subtraction and multiplication. So you got to check for all of the operations that are being used. I tried to be a little lenient about that on the homework, but on the test, I'll have to be a little stricter. So subtraction and multiplication, A, B, C, and D in Z implies that M equals BC minus AD is in Z. Don't forget to say that part, that it's actually an integer. A lot of people are writing a whole bunch of stuff, but then just not actually saying M is an integer, and N equals BD is in Z. Okay, so we've got part 2 of the definition of rational taken care of. Also, now we want to address this denominator. Since B is not equal to 0 and D is not equal to 0, by the ZPP, we know BD, N equals BD. You don't have to say N if you don't want to, but it's not 0. Okay, so we've nailed it. So Y is rational by the definition of rational. And just to emphasize, how important it is that we deal with all 3 parts of the definition. This is part 2 of the definition of rational. It's been a while since we've done this, but I'm just going to do it since I'm noticing, you might need that feedback in part 3 of the definition of rational. This, of course, is part 1 of the definition of rational. It's been a while since we've done that, so it can't really hurt. All right, and now we state our contradiction. That is really important. State the contradiction. We've got to explicitly say what we just contradicted. So we're going to say, this contradicts our assumption, or you could say hypothesis if you prefer. This contradicts our assumption that Y is irrational. And then I'll put a closing sentence, but it's actually optional. So and I'm going to use some different notation just to help you along. If X is rational and Y is irrational, and the way we can write the irrationals is the reals minus the rationals. Literally, you subtract the rationals away from the reals, and that gives you the irrationals. We see X plus Y is an element of the irrationals, which is the reals minus the rationals. So this is a new notation for the irrationals. This is actually an optional sentence, so I'm going to put a wavy blue line under that, which is going to mean optional. I don't do that very often, but I might as well show you that sometimes you don't have to write every single thing, but you definitely have to write that this contradicts our assumption that Y is irrational. Questions? Comments? Okay. Well, listen, let's look at another statement. A lot of times a statement that involves one rational and one irrational is going to have a conclusion that says some expression is irrational. But not always. Not always true. Consider this statement. I'll give you the for all. For all X and Y in the reals, if X is rational and Y is irrational, then XY is irrational. Oh, I'm just fitting it onto one line, just barely getting it on there. I should have scooted it over a little bit. It's like that stand-up comic. You ever seen John Mulaney's bit about making a happy birthday sign and he starts real big, and then he has to make it tiny at the end because birthday doesn't fit. It's really funny. John Mulaney's really funny. Anyway, so if X is rational and Y is irrational, then the product XY is irrational. Now, what we just proved is that the sum of a rational number and an irrational number is always irrational. We just proved that. But the question is the product of a rational number and an irrational number always irrational? In other words, is it true or false? And one way to kind of get your head around whether something is true or false is to write the negation, of course, and think about the negation. So let's do that. Let's write the negation. Everybody write the negation of this statement. Practice doing that. I don't want to touch that. I hope everybody wrote there exists. Such that X is rational and Y is irrational. Somebody help me finish this.
Is it and XY is rational?
Exactly. Nice, Nick. And XY is rational. All right, so that's one way to try to figure out if something is true or false, is to, look at the original, look at the negation, think about it. Can you come up with, a counterexample? But, there's another way actually to try to figure out if something is true or false. Let me show you another approach. To deciding if a universal statement is true. Try and prove it and look at the algebra involved. Try to prove it and see what happens with the algebra. Okay. So I just want to kind of show you how that can also give you clues and hints about things that might happen if you try to prove it, and that can give you clues and hints about maybe a counterexample. I mean, I think everybody in the room has figured out this is going to turn out to be false, right? I hope you're gleaning that that's sort of the point. But if we try the proof, and it's going to be by contradiction, because really a statement involving one rational and one irrational, the only way to attack it would be a proof by contradiction. So, we would assume there is a rational number X and an irrational number Y such that X, Y is rational. And we would write down the definition of rational for both of these, but somewhere along the way, we do the definitions, but we would have to somehow, try to contradict something. We'd be contradicting that Y is irrational. So, eventually we would need to set up some kind of, equations. And since XY is the expression that involves both X and Y, eventually we would say, hey, XY is equal to XY. And we would think about the fact that, okay, we're going to have to contradict the fact that Y is irrational because that's the only thing we can do with that. So we would say, okay, we're going to solve for Y, right? So we'll divide both sides by X to solve for Y. What could possibly go wrong? When we start dividing in any proof, if you start dividing both sides of an expression by some quantity, there's always something you have to be aware of and worry about. What do we always have to worry about when we're dividing, folks?
Canceling out variables.
We would cancel out variables, but yeah, in fact, this would just be like Y equals Y. But before we even do that, before we get to the canceling stage, when we're at the dividing stage, what do we have to worry about if we're dividing? What's the one number we can't divide by?
0.
Right. See, we have to worry about that. What could go wrong? Well, what if X is 0? And you see, all we know about X is that it's rational. Nobody said it's not 0, right? So the possibility is that things could go bad if we start trying to prove it, and then we realize we're dividing by X and we don't know anything about X except it's rational. And that gives us information about how we might actually go back to the negation and try to establish that the negation is true if we look at what happens when X is 0. So let's go back and look at the negation again. And let's think about what happens when X is 0. Isn't 0 an example of a rational number that exists? So what happens to X times Y if X is 0?
And that's 0.
Yeah, XY is 0, and 0 is rational. So you see, you can hit it either way. One thing, is look at some algebra, think about what might go wrong, and then think about maybe using that information to help you build a counterexample. The other thing is just to remember this advice about looking to build an example or a counterexample. Keep it simple. Keep it simple. And lots of times, folks, a problem will happen at 0. Or when we get into set theory, a problem can happen at the empty set. Those are kind of classic things you learn in mathematics, is that, hey, you got to check out what happens when X is 0. Oh, you got to check out what happens when that set is an empty set. So we can build a counterexample. We cannot disprove, sorry for the double negative, but we cannot disprove the negation because we cannot divide by 0. And there's no guarantee that we wouldn't be doing that. So that gives us insight into a counterexample. That proves the negation. See, the counterexample will actually prove the negation is true. We can't disprove the negation because, in fact, the negation is true. Here we go. Let's build a counterexample to prove this negation. This is example 2. We're giving a counterexample because we're going to prove the negation. Consider x equals 0. And let y be any irrational number. Now, clearly, 0 is rational, right? We need to have x be rational because that's what the negation says. That because 0 is equal to 0 over 1, 0 and 1 are in z, and the denominator 1 is not equal to 0. Kind of silly, but it's true. Further, and now, see, so that's part 1 where we check and make sure that our element is in the right domain in our counterexample. And now we're going to verify that this property holds, that xy is rational. We've picked any irrational. Hey, if you want, you can pick your favorite irrational number. And in a few minutes, we're going to prove square root of 2 is irrational. And you will always be able to use the fact that square root of 2 is irrational from there on out. You'll always be able to use that. Further, xy equals 0 times y equals 0, which is rational. You know, see above. We just proved it. So it's not always true that a quantity involving one rational and one irrational turns out to be irrational, but it's true a lot of times. You just got to watch out for the 0. Questions? All right. So we understand the principle of proof by contradiction, I hope. And we will review the 3 proof methods that we've learned in just a little bit. But I'd like you just to recall now a lemma, because the next thing that we're going to prove is this fact. Or we could call it a claim. Square root of 2 is irrational. Okay. We will prove this. First, let's recall a lemma. We proved this lemma last week. It was a proof by contrapositive. It was our motivating example for why proof by contrapositive is a good thing. The lemma went like this. For all n in the integers, so for all integers n, if n squared is even, then n is even. Remember that one? We proved it by contraposition. And you should review that proof. We're going to need that lemma tonight to prove the square root of 2 is irrational. So here's our proof of the fact by contradiction. Now, when we think of proof by contradiction, we think of proving, universal statements. Okay. We can actually write this as an if-then statement if we really wanted to. We could say if x equals square root of 2, then x is irrational. But sometimes it's just as easy just to think about the simple negation of the given statement. Square root of 2 is a real number. So if it's not true that square root of 2 is irrational, then that means it's rational. So the negation of the statement that square root of 2 is irrational is just super simple. It's, hey, assume square root of 2 is rational. And that is our correct hypothesis. We assume that it's rational. And we wish to show this leads to a contradiction. So proof by contradiction is kind of easy in terms of the wish. The wish is always the same. In proof by contradiction, you're always wishing to prove that there's some kind of contradiction. You may not know what it is yet, but that's what we're looking for, some kind of contradiction. Now, by definition of rational, let's just apply the definition. Square root of 2 is equal to a over b, where a and b are integers and b is not equal to 0. Okay. Now, here's actually going to be the key to the proof. I'll draw my little skeleton key picture over here. There's my skeleton key. Here's the key to the proof. Do you agree that every fraction can be written in simplest form, where we, cancel out all of the common factors besides 1, of course? Yep. So that's what we're going to assume. We may assume a over b is written in simplest form. And I'm just going to say a little bit more about what that means mathematically, i.e., that a and b have no what we call non-trivial. I mean, they got the factor 1 in common, but they have no non-trivial common factors. Okay, so we're going to make that assumption. Nothing up either sleeve here, folks. This is completely legit. We know that if we have any kind of fraction, we can always reduce it to simplest form. All right. So let's take our equation. Square root of 2 equals a over b. And let's square both sides. So we have square root of 2 quantity squared equals a over b squared. That's perfectly legitimate. So of course that lifts the radical on the left side, and on the right side we have a squared over b squared using laws of exponents. Now we can multiply both sides by b squared. That's not a problem. Okay. And we know b is not 0 anyway, or it never would have been able to be down there. Right? But anyway, 2b squared is equal to a squared. I'm going to call that equation 1. So what do we know about a squared at this point?
It's even.
It's even. Does everybody see that a squared is even? It's 2 times b squared, but b was an integer, so b squared is an integer, right? So that makes a squared even. So notice equation 1 shows us that a squared is even. Everybody with me? And now I'm going to fold this down so you can see the lemma. There's our lemma. So what do we know by the lemma? Doesn't matter if it's called N or A, right? So Kadra, what do we know? What does the lemma tell us?
That if A squared is even, that means A is gonna be even.
Exactly. A is going to be even. So let's write that down. By the lemma, and you usually do tell your readers when you're using a lemma, this means A is even. So we can write A equals 2 times K for some integer K, right? That's what it means for A to be even. Substitution into equation 1 yields, okay, so we're going to substitute in A equals 2K for some integer K back into equation 1. Let's see what happens. Two B squared equals the quantity 2K squared, right? Because A is equal to 2K. So I'll just put that in there. Well, let's do the algebra. So on the left, we still have 2B squared. The right side becomes 4K squared when we square it. And then we can divide both sides by 2, and we have B squared equals 2K squared. We'll call this equation 2. So what do we know about B squared?
It's even.
It's even. For the same reason that A squared is even, now we can say B squared is even. So equation 2 shows B squared is even. And then what do we know by the lemma?
B is even.
Yes, and the lemma tells us B is even. I claim we have a contradiction. You see what it is? Don't forget the key to the proof.
AB is already in simplest form, and if they're both even, then that means it can be simplified. So it contradicts that.
That's exactly right. Does everybody see that, what Edwin just said? A over B is written in simplest form, but A is even and B is also even. That means they both have a common factor of 2, and that's a non-trivial common factor, right? It's a factor that's in common, that's not 1, it's 2. So that's our contradiction. So let's write that up. But this means both A and B are even, which contradicts our assumption that A over B was written in simplest form. We conclude, and this is optional, square root of 2 must be irrational. And again, yeah, this is optional, so I can put my little wavy blue line under that. You don't have to put just my wavy line. You don't have to say that, but sometimes it's nice to tell your reader what you just did. Isn't that cool? And completely understandable. Questions? Comments? Well, let's take a few minutes now and review the 3 proof methods. And I have included a new document in the Good Stuff folder called Name of Proof Methods. And it's got this information right here. If we want to prove P implies Q, let's compare the proof methods that we have learned. Okay? The name of the method, the hypothesis we would take, and then what we wish to show. And then we're going to look at 2 more statements. All right, so for the direct proof method, which is the proof method we used for weeks, we assume P, right? We assume the hypothesis, which is right there, and we wish to show that the conclusion Q follows, right? Direct proof method. But proof by contrapositive is actually direct proof of the contrapositive, which is if not Q, then not P. So we assume not Q in proof by contrapositive. And what we wish to show is not P, right? Because we're proving if not Q, then not P, instead of proving if P, then Q. But they're logically equivalent, so it works. Finally, what we've just learned tonight is proof by contradiction. And we assume the negation. I've suppressed the quantifiers just to simplify this chart, okay? But I think we all know the negation of a for all statement is a there exists statement. And I think we all know by now that an if P then Q statement is a for all statement. I hope so anyway, right? So we assume the negation that P happened and not Q also happened. And the wish is that a contradiction occurs. The wish is always the same for proof by contradiction. It's just that we get a contradiction. So this is there for your reference. And like I said, I've also added a document to the Good Stuff folder and a little pointer to it in the reading page that, hey, see the new document called Name of Proof Method. And it's basically just this. Okay, questions? All right, so we have a few more minutes, and I just want you to think about 2 more statements. So the first statement would be if X and Y are rational, then X plus Y times square root of 2 is irrational. Now there is something similar to this in WebAssign. It's actually a little more complicated. No, I think it's very much like this, actually. I think they even do use square root of 2. And you may assume square root of 2 is irrational. So if you were going to try to prove this statement, you would use a proof by contradiction. Okay? And like I said, you have a WebAssign homework that you're going to have to do do this basically. So I suggest, that you do later, actually do later. Try to prove that using proof by contradiction. It'll be good practice. And then you can compare with the WebAssign to see how you're doing and kind of inform your proof writing with the WebAssign because it'll walk you through it. Here's another statement that would be proven by contradiction. And it's a true statement, obviously, otherwise we couldn't prove it. And that is that there is no smallest positive real number. The way to prove it is to assume that there is a smallest positive real number and get a contradiction. So I want to show you a picture. Oops, I've given it away. Oh no, I should have erased this. You didn't see this. Assume this R is the smallest positive real number. Okay, so I mean, just imagine we're looking at, the real number line with a magnifying glass and we're zooming in and we're zooming in and we're zooming in and we're saying this is the smallest positive real number. How could we contradict that?
The number in between 0 and R.
Yeah, that's the point is if there's any space between 0 and R, it amounts to an infinite amount of space between 0 and R because there are as many numbers between 0 and R, not including R, as there are between 0 and positive infinity. And that is the weird thing. That shows exactly sort of the limitations of our ability to understand infinity. But yeah, and so how do we build a number that's between 0 and R? So it'll be smaller than R, but it'll still be to the right of 0, so it'll still be positive. What would be a way to do that? As if you didn't already see it. But there's more than one way to do it. Like the easy way is just take R and split it in half. But that is not the only way. Subtracting something from R isn't going to work out because then I would pick a smaller R and then when you subtract something from it, it would turn out to be a negative number. So subtracting is not going to work, but splitting R by 2 or 3 or whatever you like. But there are other ways to build numbers that are smaller than R. Can you think of another way to build a number that's in between 0 and R?
R squared.
Very close. You're so close.
The square root.
Yes, the square root. Yeah, you could take the square root of R. So any way you slice it, the game is, to do something that you can prove really builds a positive number that is actually smaller than R. Now, proving that R over 2 is positive is easy. R is positive, 2 is positive, and we can just say, hey, a positive divided by a positive is positive. So proving that it's positive is the easy part. Proving that it's smaller than R just takes a little bit of trickiness. But the first thing to do is to prove that, you could try it with square root of 2 and you could do it that way too. That, the number that you're picking is really positive, but that it's smaller than R. And seeing that contradicts the notion that R is the smallest, right? And I have included, I'm going to include an extra page of notes. You can play with this and work on it. I'm not going to show you the extra page of notes, but I will post well, they're already up, but I'm going to repost the extra page of notes that kind of points you to how to prove that R over 2 really is smaller than R. So it really tucks in between here. But I like the idea of trying to prove square root of 2 is smaller than R. I think that would also be fairly easy to do. So there is a WebAssign problem also that's sort of a twist on this. The WebAssign problem is to prove that there is no largest negative real number. And remember, numbers as they go to the left get smaller by definition. If a number y is to the left of x on the number line, then we say y is less than x. So any number that's, really close to 0 is getting toward the largest negative real number in terms of not magnitude, but what we consider larger numbers. Larger numbers are to the right. So there's a proof that you have to kind of work on, sort of like, fill in the blanks or pick your statements to fill in the blanks to prove that there is no number that is the biggest of all the negative real numbers. Like, because it's kind of like here, no matter, you zoom in, you zoom in, you zoom in, there's always going to be space between whatever number you pick and 0. And you can tuck in another number that's still negative, but bigger than the supposed largest negative real number. So have fun with those. Like I said, I gave you a little more time this week to work on the WebAssign since you've got a quick turnaround on your special homework. The mini homework, number 8, is just 2 questions, but I did want to give you a little more practice. Folks, if you're not turning in your special homework, if you need to talk about that, stick around, people can go in the waiting room and take turns. I wouldn't be recording that, obviously. We could have a private discussion if you need to. But I'm concerned with the percentage of students that just aren't even opening the homework. Those of you who are doing the homework, yay, and you're getting your feedback, you've got your graded homework number 6 back. I'll be grading homework number 7. Probably won't get it graded before Wednesday because I've got a ton of stuff to do between now and Wednesday. But I'll get it graded, over the toward the end of the week, and I'll also be grading your mini homework. And everybody knows how to upload the feedback, right? Not just the grade, but everybody's getting your eyes on the PDFs that I've been uploading with all of the comments. And I hope I was kind of amazed. I think maybe a couple of students weren't able or just weren't aware, that this whole semester I've been actually grading your work so that you could get comments. That's supposed to help you. So please take a look at that stuff and make an appointment if you need to. This weekend I'll be around to help out if you need a little extra time. And if you're wondering what to study for, go through all the class notes. Make sure you know the definitions like the back of your hand. Make sure you know the definitions, folks. Do all the do laters. Any do like these, really try to do them. All the do laters. And, ideally over the last 4 weeks, you would have been coming into office hours and saying, hey, I got this homework problem wrong. Can you sort me out? I don't understand the comments, We'll rewrite your homework problems, now. Practice rewriting them if you didn't make the score that you wanted to make on them. And if you want to bring them into office hours, we do have a few more hours of office hours before the test. So I would definitely, look over special homework, make sure you've done your WebAssign, do all the do laters, make sure you know your definitions. And between all that, I think you will have gotten enough practice to do okay on test 2. Ironically, students generally find test 2 a little bit easier because even though it's proofs, you've already done the worst. You sat for the very first test, right, and survived it. So believe it or not, grades actually tend to go up a little bit on test 2, especially if you've been doing your homework. So I hope that'll be true for you. Any comments, questions? Thanks for playing. All right, I'm going to stick around. We do have an office hour, not tonight, but we have one on Wednesday. If you need an office hour tomorrow night, email me, right? I could also do one Wednesday morning. So if you need an extra office hour, I'm giving it a linear algebra office hour actually at 8. But I'm going to stick around. I'm going to stop recording. I'm going to stick around for you if you want to visit or talk about what's going on. All right. Thanks for coming to class.